In 1967, an astronomer named Jocelyn Bell discovered a strange signal in data from a radio telescope in Cambridge, England. Pulses of radio emission had appeared in her data, arriving just over once a second. The pulses appeared with astonishing regularity, like a perfectly ticking clock, and were unlike any signal we had ever seen from the sky. Their timing was so precise that Bell and her colleagues jokingly nicknamed the mysterious source of these pulses LGM, for Little Green Men. In the next 2 months, Bell found 3 more of these little green men, all perfectly pulsing radio sources, and all coming from different distant places in our own galaxy. We know today that the signals discovered by Bell were not coming from extraterrestrial timekeepers. Instead, these pulses were the very first observations of something called a neutron star, the tiny and dense remnant left behind by the supernova death of an enormous star many times the mass of our Sun. Neutron stars have been intensely studied in the 50 years since Jocelyn Bell's observations, and her discovery sparked a new wave of interest in searching for their long-predicted and mysterious cousins, black holes. This program will focus on Jocelyn Bell and the other astronomers that led to the search for neutron stars and black holes. First, we'll talk about what neutron stars and black holes actually are. Where do they come from and how do they work? Next, we'll cover how we actually observe these strange objects, measuring signals from their magnetic fields and interactions with companion stars. Finally, we'll discuss work going on today by heroic teams of scientists using cutting-edge techniques to study neutron stars and black holes and learn about stellar death, gravity, and our own universe. Neutron stars are created during the deaths of massive stars. Remember, a star is considered massive if it has at least 8 times the mass of our own Sun. And because of these large masses, the stars lead relatively short lives, dying as supernova after only about 10 million years. In those supernova deaths, newly formed iron cores lose the star's lifelong battle between the inward pressure of gravity and the outward push of energy produced in nuclear fusion. When this happens, the star's core implodes, and the star's outer layers bounce off the imploding core and produce a spectacular rebound shock. The bounce and shock give us the supernova explosions we talked about a couple of programs ago. But that collapsed core remnant left behind at the heart of the supernova is a neutron star. Neutrons are subatomic particles with a neutral charge, joining positively charged protons and negatively charged electrons as the tiny ingredients that make up individual atoms. Normally, neutrons are bound up with protons in the nucleus at the heart of an atom. However, at the incredible high temperatures achieved when a massive star dies, these atoms are broken apart. The neutrons become free particles and the protons and electrons combine to form even more neutrons. The result is a hot neutron soup. This soup forms a neutron star thanks to the Pauli exclusion principle of quantum physics. This principle states that subatomic particles, like neutrons, can't occupy the same quantum state within a system. In other words, 2 neutrons with identical physical properties can't occupy identical locations in space. If you try to squeeze them together in a tiny space, they'll push back, exerting an outward pressure. In the incredibly dense interior of a neutron star, further collapse would start shoving neutrons too close together with their neighbours, putting them at risk of violating this principle. To avoid this, the neutrons create an outward pressure so powerful that it actually halts further gravitational collapse. For the size scales we are talking about, the result is an unbelievably tiny and dense remnant of the original star's core. What we know is a neutron star. Neutron stars are only about 12 miles across, the size of a small city. You could drive all the way around a neutron star in under an hour. They're also the densest objects that we know of in the universe. If you were to scoop up a single teaspoon of material from a neutron star, it would weigh more than Mount Everest. The entire neutron star can be up to twice as massive as our own Sun. That mass is just crammed into an extremely small package. The surface of a neutron star is also very hot, over 1,000,000 degrees Fahrenheit. That's 100 times hotter than the surface of our Sun. Finally, these neutron stars are rotating incredibly fast. We've just compressed the mass of an entire rotating stellar core down into the area the size of New York City. You've seen what happens when a spinning figure skater pulls in their arms, and the same principle applies here. By bringing their own mass closer to their axis of rotation, they're able to spin faster and faster. Now imagine doing this on the scale of a massive star. The fastest rotating neutron stars will complete several hundred rotations in a second. We think that the surface of a neutron star is composed of a thin crust of ionized atoms and electrons. But as we go deeper, we mainly find neutrons, and the environment deep inside these stars is so extreme that we still know very little about how to mathematically describe and model this sort of matter. When a neutron star is born during a supernova, we're not just compressing matter in neutrons, we're also compressing the magnetic field of the original star. Most stars have pretty weak magnetic fields, but as we squeeze them into a neutron star, they can become incredibly powerful. These strong magnetic fields can funnel jets of particles out along the two magnetic poles of the neutron star. The acceleration of those particles is so extreme, speeding away from the star at close to the speed of light, and whirling along the curved lines of the star's magnetic field, that they actually emit photons as they move. This phenomenon is known as synchrotron radiation, and in a neutron star it generates powerful beams of radio frequency light shooting out of the magnetic poles. We know that the magnetic poles of a star or planet aren't always aligned with its rotational axis. We've seen this here on Earth. Our magnetic poles aren't at the northern or southern poles, but tipped slightly. This is why we sometimes talk about the difference between the true north and magnetic north. If you now imagine this in a neutron star, spinning around its rotational poles and shining bright light beams of radio frequency light along its tilted magnetic poles, you get this. It acts like a searchlight from a lighthouse or the flashing light on top of an emergency vehicle, producing a flash every time one of those bright radio beams sweeps past. We detect these flashes as radio pulses, coming from the neutron star, with the rate of pulsation telling us how fast the neutron star is spinning. With the slowest spinning stars we'll detect maybe a couple of pulses a minute, but the fastest will emit hundreds of pulses per second. That's faster than a hummingbird beating its wings. These rapidly flashing neutron stars are known as pulsars. This is what Jocelyn Bell and her colleagues found in their data. Of course, they didn't know this at first. At the time, neutron stars had been predicted by theoretical physics, but nobody had actually seen any sign of them, and nobody had predicted that they might produce these perfectly timed pulsations. The signal at first was so perfect, too perfect, that Bell's first step was to ensure that she hadn't found something too good to be true. This sort of caution makes perfect sense. It's always important for astronomers to be careful when they find something new and unexpected. We want to be absolutely sure that the data we're collecting is truly a signal from deep space, and not something a bit closer to home. This is particularly challenging in radio astronomy, when you remember that so many objects used in our everyday life on Earth can produce radio interference. fluorescent lights, cordless phones, and even the spark plugs used in petrol-powered car engines can all be picked up by radio telescopes. The Parkes Radio Telescope in Australia spent years detecting strange short bursts of radio emission. It wasn't until 2015 that a group of researchers realized that these bursts tended to happen around mealtimes, and they tracked them back to microwaves at the facility. Some radio telescopes, like the Green Bank Observatory in West Virginia, avoid this by operating in radio quiet zones, banning cell phones and microwaves, and even requiring diesel-only vehicles near the facilities, since they don't have spark plugs. Jocelyn Bell quickly realized that her pulsars were the real deal. Despite skepticism from her colleagues, she tracked the first signal that she discovered for months and connected it to a source that rose in the evenings along with the rest of the night sky. She and her colleagues realized that these pulsations were likely connected to objects like neutron stars, and published their results. The discovery was met with enormous excitement and curiosity, and ultimately received a Nobel Prize in 1974. Unfortunately, Bell herself was not awarded this Nobel. Her thesis advisor and another colleague received the prize instead. In fact, out of the 212 Nobel Prize winners in physics up through the year 2019, only 3 have been women. Despite this, Bell went on to a long and distinguished career and was awarded the 2018 Special Breakthrough Prize in Fundamental Physics in recognition of her extraordinary scientific achievements. After Jocelyn Bell's discovery, there was a huge resurgence of interest in studying neutron stars and other objects like them, things left behind after the collapse of massive star cores. If a neutron star exists, odds were that something even more extreme and unusual might be discovered: a black hole. Black holes represent the ultimate extreme of what we know about physics, gravity, and space-time. Sometimes, after the collapse of a very massive star's core, even quantum physics can't battle the immense inward pressure of gravity. In a case like this, the core will keep collapsing, forming a tiny and dense object that severely warps space-time. Gravity in this tiny corner of space-time becomes so strong that nothing can escape it, not even light. To understand what this means, imagine a rocket being launched into space from the surface of the Earth. In order to break free from Earth's gravitational force and reach outer space, the rocket needs to travel at what we call escape velocity. This means the rocket must be travelling about 25,000 miles per hour, or about 7 miles per second, to leave the Earth. Objects with stronger gravity have a higher escape velocity. For that same rocket to escape from the gravitational pull of our Sun, it would need to be travelling nearly 4 times faster, covering more than 380 miles in a single second. The gravity of a black hole is so strong that even light itself, travelling at 186,000 miles per second, isn't moving fast enough to achieve escape velocity. Instead, that light and everything else becomes irrevocably trapped inside the warped region of space-time around the black hole. It would be like trying to launch yourself to Mars by jumping into the air. You simply can't jump at the speed that will let you escape Earth's gravity. Inside a black hole, even jumping at the speed of light wouldn't be enough to escape. Astronomers have toyed with the idea of objects like this for decades. The earliest prediction of a black hole can be traced back to the 18th century. In the early 20th century, Albert Einstein's general theory of relativity sparked a new wave of interest in black holes from theoretical physicists, who began studying what they could do to space-time and light, and how we might eventually observe them. Still, it was Jocelyn Bell's discovery that paved the way for astronomers hoping to actually observe and prove the existence of black holes. When not even light can escape from an object, it's easy to see why astronomers might have a hard time studying them. Fortunately, Einstein's theories gave us the tools for predicting what black holes might do to their surroundings, and this ultimately gave us our first glimpse of a black hole. In 1964, a team of astronomers launched a sounding rocket from the White Sands Missile Range in New Mexico. The rocket was carrying a special instrument designed to detect X-rays coming from deep space. The suborbital rocket spent only a few minutes above the Earth's atmosphere, but in that short time it surveyed the sky and found the first evidence of a strange object in the constellation Cygnus. Something in that part of the sky was emitting X-rays, and those X-rays seemed to be varying with time. Later observations with satellites and other telescopes revealed the X-rays appeared to be coming from a bright blue massive star named Cygnus X1. This surprised and confused astronomers at first, since stars don't typically emit many X-rays by themselves. It wasn't until 1971 that three astronomers, Louis Webster and Paul Murden and Charles Bolton, working separately, discovered that this blue star had a close neighbour, what's called a binary companion. What's more, the binary companion seemed to be invisible and very massive, 15 times as massive as our Sun. They proposed that the companion must be a black hole. It was far too massive to be a neutron star, and that the changing X-rays were coming from matter being dragged from the blue star into the black hole. For many years astronomers continued to study Cygnus X1 and other objects like it. We've since discovered many more X-ray emitting binaries, with bright stars and neutron star or black hole companions. Every detail of these companions matches the predicted properties of black holes. Still, most astronomers wanted incontrovertible evidence that black holes truly existed. Another exciting discovery came in 1995, when astronomers began tracking the motion of stars orbiting what was believed to be a supermassive black hole at the centre of our own Milky Way. Today we believe that most galaxies have supermassive black holes near their centres. We're still not sure how black holes like these are made, but most astronomers believe that they form by merging with other black holes or trapping huge amounts of matter in the warped space-time surrounding their masses, growing over time. This leads to black holes containing huge amounts of mass. The black hole believed to be at the centre of the Milky Way would be as massive as 2.6 million suns. The stars near this black hole are careening through space in tight and high-speed orbits. From watching them move, astronomers could see clear evidence that a huge amount of invisible mass was concentrated at the centre of our galaxy. It was another strong piece of evidence for the existence of black holes. The most exciting observation of a black hole happened in 2019, when a team of 347 astronomers announced they had captured the first actual picture of a black hole. The discovery happened thanks to an incredible collaborative effort on a project known as the Event Horizon Telescope. This super telescope was made up of 8 radio observatories scattered across the face of the planet, using a technique called radio interferometry, the same technique we learned about in our program on radio telescopes. Astronomers synchronized these observations to turn the Earth into one giant radio telescope. In April of 2017, this worldwide telescope collected data of the supermassive black hole at the centre of a nearby galaxy known as M87. The galaxy was about 53 million light-years away, and the supermassive black hole was 6.5 billion times as massive as our Sun. Still, the edge of the black hole was thought to be barely larger than our solar system. The picture they took was equivalent to reading the date on a quarter in Washington, D.C. while standing in Los Angeles. The first image of a black hole was a revolutionary achievement, confirming many long-held theories of how gravity and black holes should work. It also would not have been possible without the hundreds of people on the team ensuring that every last detail of the telescope and observations were planned and executed to perfection. The radio waves emitted by the superheated material around a black hole will bounce right off water molecules in our atmosphere. This means to observe them we need to use telescopes built in some of the driest places in the world, like the Atacama Desert in Chile, southern Arizona, the summit of Mauna Kea in Hawaii, and the desert-like climate of the South Pole. The telescopes used in the Event Horizon telescope were already in these dry and remote locations, but they weren't originally designed to work together. Each one was built separately and spent most of its time operating as an independent observatory. It took years for team members to retrofit each individual telescope with customized equipment so the Event Horizon telescope could operate as one system. Each site in the array also had its own quirks. One telescope in Hawaii observes from under a Gore-Tex shroud to protect it from wind, blowing sand, and even bird droppings. A Spanish telescope in the array is equipped with its own de-icing system so it can quickly recover from mountain storms. The Atacama Large Millimeter Sub-Millimeter Array in Chile is at an altitude of just over 16,000 feet. Astronomers and engineers working there need supplemental oxygen to work safely in the thin air. For interferometry to work, we also need to know exactly when and where each piece of data is captured. This means equipping each telescope with an atomic clock and tracking its location with military-grade GPS. Keeping track of a very large telescope may sound like a simple job, but the very ground they're built on will sometimes move. Hawaii and Chile are famously earthquake-prone, and the South Pole telescope is built on the Antarctic ice sheet, which drifts more than 30 feet every year. Getting all 8 telescopes to observe the supermassive black hole in M87 at the same time also meant waiting for perfect weather at 8 different sites around the globe. Team members around the world had to wait anxiously for a go-no-go decision every night. With thunderstorms in Mexico and windy weather in Arizona, grinding worldwide observations to a halt for 2 days in the middle of the team's work. Finally, data from the different telescopes can't just be passed by email or uploaded to a server. By the time the telescopes were done observing M87's supermassive black hole, they had generated 5 petabytes of data. That's equivalent to this program being 229 years long. You'd love that, wouldn't you? Processing the data from all 8 sites meant shipping the hard drives around the world. Even moving the drives was easier said than done. The observations happened during Antarctic winter, when there are no flights to or from the continent, so the South Pole data had to wait until November before it could be flown back to one of the team's supercomputers. At the supercomputers, astronomers and computer scientists on the team then spent months perfecting techniques for analyzing and combining the data. In the end, it took several hundred heroes of astronomy, physicists, engineers, computer scientists, astronomers, and the many people who operated and run the 8 telescopes around the world to capture humanity's first groundbreaking glimpse of a black hole. Jocelyn Bell's discovery of pulsars gave us the first observational evidence that objects like this could exist. The excitement that followed her discovery led to a new wave of research on black holes. Objects like neutron stars and black holes represent fascinating extremes of physics that warp space-time and strain our understanding of how stars die and how the universe works. Since their discovery, we've learned a great deal about neutron stars and black holes in their own right. They've also become invaluable tools for studying gravity and the very nature of space and time itself. In our next program, we'll begin exploring Einstein's general theory of relativity and some of the incredible ways that observations of neutron stars and black holes have been used to test some of Einstein's biggest ideas. Well, that's it for this week. Everybody please stay safe and look after each other, and I'll see you again next week. Bye for now.